Section 6.3, Inverse Trigonometric Functions. In this section, we're going to discuss the construction of the inverse trigonometric functions and how to evaluate them and how to use them to solve problems. To start, how do we create the inverse trig functions? If you recall from earlier in this course, a function only has an inverse if and only if it's one-to-one, meaning for every y value, there's exactly one x value or input that will produce it. By definition, periodic functions are not one-to-one. They horribly fail the horizontal line test because of their period. But if you recall from the beginning of the course, whenever we were dealing with non-one-to-one functions, such as the quadratic function, we can truncate the domain in such a way that makes the function we're trying to find the inverse for one-to-one. So how do we truncate the domain of our trig functions? For sine, we're going to truncate our domain to negative pi over 2 to pi over 2, and this will be a closed interval. If you observe the graph below, there's our sine function with our domain restricted to negative pi over 2 to pi over 2. Notice on this domain, sine of x is 1-to-1. Cosine is going to be restricted to 0 to pi. Looking at the graph below, which has the cosine function restricted to the domain of 0 to pi, we can see under this domain, our function is 1-to-1. Lastly, for tangent, we're going to restrict our tangent function to the open interval, negative pi over 2 to pi over 2. Very similar to the restriction of sine, the only difference is tangent is going to have an open interval. That's because tangent of x is undefined at negative pi over 2 and pi over 2. To the right, notice the graph of our tangent function restricted to the interval negative pi over 2 to pi over 2 is 1-to-1. So while sine, cosine, and tangent without these restrictions are not 1-to-1, when we do restrict them to these respective domains, they do become 1-to-1. Therefore, an inverse function will exist. If we look at the table here on the top left, we can see each inverse trig function, their domain and range. The inverse trig functions are going to be denoted similar to the notation we've used for inverse functions by putting a -1 as a superscript to denote that we are working with an inverse function. The domain of each of our inverse trig functions come from the range of our original trig functions. If we think about the graphs of sine and cosine, they oscillate between the values of -1 and 1. So sine inverse and cosine inverse will have a domain of -1 to 1 because that is the range of sine and cosine. Tangent inverse is going to have a domain of the set of all real numbers, since the range of the tangent function is the set of all real numbers. The range of our inverse trig functions come from how we are truncating the domain of our original trig functions. Sine, we restricted to the interval negative pi over 2 to pi over 2 in order to make it 1-to-1. So the range of sine inverse is going to be negative pi over 2 to pi over 2. Cosine, we restricted to 0 to pi to make it 1-to-1. So the range of cosine inverse is from 0 to pi. And the range of tangent inverse is going to be negative pi over 2 to pi over 2 because of how we restricted the domain for the tangent function. Please pay very special close attention to the domain and the range of each of these trig functions, especially with the domain of sine and cosine inverses. That tells us we can't plug in any number we want to try to evaluate it. We also have to pay very close attention to the range, especially if we want to use the unit circle to help us. More specifically with sine inverse and tangent inverse, we're going to have to work quite a bit with coterminal angles to help us evaluate. Now, how do we evaluate our inverse trig functions? We have to reverse the definitions of sine, cosine, and tangent based on the unit circle. If we try to evaluate sine of an angle, the output was the y-coordinate of the point associated with that angle. If we reverse inputs and outputs for the inverse, the output of sine inverse t is going to be the angle, and the input of sine inverse t is going to be the y component associated with that angle. For example, let's say we're trying to evaluate sine inverse of root 2 over 2. If we take a look at what sine represents the y component of a point on the unit circle. So to evaluate sine inverse of root 2 over 2, I want to try to find points on the unit circle with a y component of root 2 over 2. Now, if we analyze our unit circle, we see two angles. We see pi over 4, and we see 3 pi over 4. But what should be our answer to sine inverse of root 2 over 2? Since we're defining an inverse function, we should only have one answer. If we pay attention to the range, our range is between negative pi over 2 and pi over 2. 3 pi over 4 falls outside of that range, but pi over 4 is within the range. So the answer to sine inverse of root 2 over 2 is pi over 4. Next, for cosine inverse, the output of cosine inverse of t is an angle, and the input is the x-coordinate of that point associated with that angle. So if I want to evaluate cosine inverse of -1/2, since we're working with cosine inverse, the -1/2 would represent an x component of a point on the unit circle. If we turn our attention to the unit circle, we can see 2 points with an x component of -1/2, that being 2 pi over 3 and 4 pi over 3. But if we pay attention to the range of cosine inverse, the range is between 0 and pi. 4 pi over 3 does not fit in that range, but 2 pi over 3 does. So cosine inverse of -1/2 will be equal to 2 pi over 3. Evaluating tangent inverse is a little trickier than sine inverse or cosine inverse. The output of tangent inverse of t is still an angle, but the input this time is going to be the quotient of the y and x components associated with that angle. Suppose I want to evaluate tangent inverse of 1. Because I'm working with tangent inverse, the input of 1 means I'm trying to find a point whose y divided by x will equal 1. In order for the quotient to be 1, that means I want x and y to be the same value. Going to my unit circle, I can find 2 points where y divided by x will be 1. That'll be root 2 over 2, root 2 over 2, and negative root 2 over 2, negative root 2 over 2. But now, which would be the correct answer? Going to the range of tangent inverse, which is between negative pi over 2 and pi over 2, 5 pi over 4 does not fit in that range, but pi over 4 does. So tangent inverse of 1 is equal to pi over 4. Next, we're going to evaluate sine inverse of -1/2. Here, we're trying to find points with y components of -1/2 because we're working with the sine inverse function. And here, we can find two angles where the y component is negative 1/2, those being 7 pi over 6 and 11 pi over 6. The problem is these angles are too big for my range of sine inverse of t, because my range is between negative pi over 2 and pi over 2. But keep in mind, we can work with coterminal angles. Since our angles that we have right now are too big, let's subtract 2 pi to make them a little smaller. And what we get is that our 2 points that have a y component of negative 1/2 are also associated with negative pi over 6 and negative 5 pi over 6. But negative 5 pi over 6 is too small. But negative pi over 6 does fit in the range. So sine inverse of negative 1/2 is equal to negative pi over 6. One thing to note about sine inverse, because our range is between negative pi over 2 and pi over 2, our angles will always be in quadrants 1 or quadrant 4. So we won't ever have to look in quadrant 2 or 3 to evaluate sine inverse. But keep in mind, if our angle is in quadrant 4, then we do have to look at a negative coterminal angle for our answer. Next, we're going to evaluate tangent inverse of negative root 3. Tangent inverse and sine inverse have very similar ranges. The only difference is one closed and the other's open. So just like with sine inverse, I would only look at quadrants 1 or 4 for the answer. I'm going to do the same thing with tangent inverse. I'm only going to look at quadrants 1 or 4 for the answer. But I also have to keep in mind that the quotient of y over x has to be negative root 3. If I look at the points down here in quadrant 4, if I do negative root 3 over 2 divided by 1/2, that does give me a quotient of negative root 3. However, 5 pi over 3 is too big. Just like with sine inverse, we're going to subtract 2 pi to make the angle negative. And when we do, we get negative pi over 3. So tangent inverse of negative root 3 is equal to negative pi over 3. Next, we'll evaluate cosine inverse of negative 1, which means I'm trying to find a point whose x-coordinate is negative 1. And looking at the unit circle, I see pi is associated with the point negative 1, 0. So cosine inverse of negative 1 will be equal to pi. Next, we're going to evaluate sine inverse of 1, which means we're trying to find a point with a y component of 1. Looking at our unit circle, we only see one such point, which is associated with pi over 2. Pi over 2 is within our range, so sine inverse of 1 is pi over 2. Next, we'll evaluate tangent inverse of root 3 over 3. Since root 3 over 3 is positive, we'll look for our answer in the first quadrant due to the range of tangent inverse. So we want to be able to divide y and x components of our points to give us root 3 over 3. If we take a look at the points and coordinates of pi over 6, if we do y divided by x, we will get root 3 over 3. So tangent inverse of root 3 over 3 is pi over 6. Next, sine inverse of 0. So we're trying to look for points with a y component of 0. We do see two such points, negative 1, 0 and 1, 0. But since pi is outside of our range, while 0 is in our range, then sine 0 equals 0. Last, we'll evaluate cosine inverse of negative 3. If we look at our unit circle, try to find an x component of negative 3, we will not be able to find one. The smallest value of x for any point on the unit circle is negative 1, while the largest x value of any point will be positive 1. And this is why we have our range of cosine inverse between negative 1 and 1. There is no point on the unit circle that can have an x component of negative 3. So since negative 3 is not in the domain of cosine inverse, then cosine inverse of negative 3 will be undefined. Due to the restrictions of the domain and range of the trig functions when defining their inverses, we have some very interesting interactions between a trig function and its inverse when it comes to function composition. Sine of sine inverse of x and cosine of cosine inverse of x will only equal x when x is between negative 1 and 1. Ideally, we always want to think these inverse trig functions and trig functions can't swap with each other willy-nilly. However, if we think about how function composition behaves, first we would have to evaluate the sine inverse and cosine inverse first. If x is outside of the interval negative 1 and 1, then the sine inverse or cosine inverse is undefined. And if the sine inverse and cosine inverse is undefined, then by definition of the composition of trig functions, the entirety of the composition is undefined. On the other hand, tangent of tangent inverse of x will always equal x, no matter what value of x we pick. This is because the domain of tangent inverse of x is the set of all real numbers. So no matter what we plug in the tangent inverse of x, it's always going to be defined. As for the next three, sine inverse of sine of x will only equal x if x is between negative pi over 2 and pi over 2 inclusively. This is because the range of sine inverse is negative pi over 2 to pi over 2 inclusive. So if x is outside of that window of negative pi over 2 to pi over 2, then sine inverse could never equal x. Something similar happens for the other two variations of an inverse composed with its original. Cosine inverse of cosine of x will only equal x if x is between 0 and pi. This is because the range of cosine inverse is 0 to pi. And tangent inverse of tangent of x will only equal x when x is between negative pi over 2 and pi over 2. And again, this has to do with the restriction on the range of the inverse trig functions. When it comes to a trig function composed with its inverse, if x is not in the listed domain above, then this composition is undefined. As we discussed before, the first thing that would have to be evaluated is the sine inverse or cosine inverse or tangent inverse. So if x is not within the range of the sine inverse, cosine inverse, or tangent inverse, then the entire composition is undefined. On the other hand, for the other three, if x is not listed in the domain, one option is we can find an angle that is within the proper range, such that f of x will equal f of theta, where f represents the inner trig function. This would be working with reference angles and coterminal angles to help us find a different angle that'll still give us the same trig function value. Now to find the exact value of sine inverse of 1/3. Since we're evaluating sine of sine inverse, we want to check to make sure the 1/3 is between the negative 1 and 1, as indicated by the top left rule. Since 1/3 is between negative 1 and 1, then according to our composition properties, the sine and sine inverse will cancel, leaving us with 1/3. Next, tangent inverse of tangent pi over 3. According to the bottom right rule, tangent inverse and tangent cancel out only when our input is between negative pi over 2 and pi over 2. Since pi over 3 is between negative pi over 2 and pi over 2, by the property, our expression will equal pi over 3. Next, cosine inverse of cosine pi over 5. This composition we see in the center right, so the cosine inverse and cosine will only cancel out if our input is between 0 and pi. Pi over 5 is between 0 and pi, so cosine inverse of cosine pi over 5 will equal pi over 5. Next, sine of sine inverse of 3. If we were to use the top left rule, that is only valid if our input's between negative 1 and 1. However, 3 is not between negative 1 and 1, and 3 would cause our sine inverse to be undefined. So sine of sine inverse will be undefined. It's very tempting to just cancel out the sine of sine inverse and say it equals 3. It is impossible to get a value out of sine inverse of 3, and it's impossible for sine of anything to ever equal 3. Next, tangent of tangent inverse of negative 1. If we look at the bottom left rule, we know that tangent and tangent inverse will cancel out for all x. So tangent composed with tangent inverse will always cancel out, meaning tangent of tangent inverse of negative 1 will equal negative 1. Now, cosine inverse of cosine of 3 pi over 4. In the center right column, we see that composition will equal x only when x is between 0 and pi. 3 pi over 4 is between 0 and pi. So cosine inverse of cosine 3 pi over 4 will equal 3 pi over 4. Next up, tangent inverse of tangent negative pi over 4. According to the bottom right rule, they will cancel out only when our input's between negative pi over 2 and pi over 2, which negative pi over 4 is in that range. So tangent inverse of tangent negative pi over 4 equals negative pi over 4. Next, we'll take a look at cosine inverse of cosine negative pi over 3. If we take a look at our center right rule, cosine inverse of cosine of x will only equal x if x is between 0 and pi. But negative pi over 3 is not between 0 and pi. So we can't say that this composition equals negative pi over 3. Negative pi over 3 is not a value cosine inverse can produce. Now, that doesn't mean that this is undefined. So from here, there's a couple different ways we can go about this. We can either try to evaluate this directly, evaluate the cosine of negative pi over 3, then the cosine inverse of that answer. Or we can use our properties to try to rewrite the cosine of negative pi over 3 into cosine of some angle that will allow us to use our center right property. So focusing on the cosine of negative pi over 3, I could use coterminal angles, but the coterminal angle of negative pi over 3 that would be produced by adding 2 pi would be 5 pi over 3. And 5 pi over 3 still doesn't fit in our valid values for x. Now, I could use coterminal angles and reference angles if I wanted to. That's one option. But an easier option is we could use cosine's even odd properties. Recall, cosine is an even function. So cosine of negative pi over 3 equals cosine of pi over 3. So cosine inverse of cosine of negative pi over 3 is equal to cosine inverse of cosine of pi over 3. Now I can apply my property from above. And cosine inverse of cosine pi over 3 would equal pi over 3. Another approach we could take to rewrite the cosine of negative pi over 3 is we could use a combination of reference angles and coterminal angles. Cosine of negative pi over 3, thanks to either the periodic property or coterminal angles, by adding 2 pi to our negative pi over 3, we get that cosine of negative pi over 3 equals cosine of 5 pi over 3. The problem is 5 pi over 3 is still not in the interval 0 to pi, but we do know 5 pi over 3 is in quadrant 4. So we know our cosine of negative pi over 3 or cosine of 5 pi over 3 is a positive quantity. In what other quadrant is cosine positive? That would be over in quadrant 1. And this is where reference angles come into play. The reference angle of 5 pi over 3 would be located between our terminal side and the positive x-axis, and that would be an angle of pi over 3. So an angle in quadrant 1 that also has a reference angle of pi over 3 would be the angle pi over 3 itself. Now, because they're on the same right half of my coordinate plane, they are going to have the same x value, but opposite y values. The one in the first quadrant would have a positive y, while the second quadrant would have a negative y. But because we're working with cosine, that's not important. What's important is the x value. Since 5 pi over 3 and pi over 3 have the same x component, despite different y's, then cosine of 5 pi over 3 will be equal to cosine pi over 3. And we're in the same situation as we were before. Now, it did take a little bit longer, but sometimes you may not be able to utilize the even odd property so nicely. Our cosine inverse and cosine cancel, still leaving us with pi over 3. Now we're going to figure out the exact value of cosine inverse sine of 3 pi over 4. Unlike the previous examples, we're not composing a trig function with its own inverse, but we can still manipulate our expression in order for us to use those properties we learned prior. This only works because sine and cosine are cofunctions. If I replace the cosine or the sine with tangent, I would then have to evaluate through brute force or with a calculator. If we apply the cofunction identity to sine of 3 pi over 4, we get that sine of 3 pi over 4 equals cosine of pi over 2 minus 3 pi over 4. And pi over 2 minus 3 pi over 4 is negative pi over 4. Unfortunately, negative pi over 4 is not within the interval 0 to pi, so we can't cancel out the cosine inverse and cosine just yet. But similar to one of our methods that we used in the previous slide, cosine is an even function. So cosine of negative pi over 4 is equal to cosine of pi over 4. Pi over 4 is in the interval 0 to pi, so we can cancel out the cosine inverse and the cosine, giving us pi over 4. Next, we'll evaluate sine inverse of cosine 4 pi over 5. Because 4 pi over 5 is not on the unit circle, we are a little bit more limited in what we can do to find the exact value. But just like with before, we can apply the cofunction identity to the cosine of 4 pi over 5, and cosine of 4 pi over 5 would equal to sine of pi over 2 minus 4 pi over 5, and pi over 2 minus 4 pi over 5 is negative 3 pi over 10. Negative 3 pi over 10 is in the interval negative pi over 2 to pi over 2, so we can apply our properties that we saw in the previous slide, and the sine inverse and sine cancel out, meaning our answer will be negative 3 pi over 10. Now we're going to evaluate compositions of trig functions and their inverses in the form of f of g inverse of x, where f and g are trigonometric functions. So here what we're doing is our inner function is going to be an inverse trig function, while the outer function in the composition will be a trig function. And if you look at the examples below, notice how we're mixing different trig functions together. We have cosine and sine inverse, sine and tangent inverse, cosecant and cosine inverse. Unfortunately, there isn't a way for us to rewrite the sine inverse, tangent inverse, or cosine inverse in order to allow us to set up for the properties like we did in the previous example. In order to help us evaluate, we're actually going to use triangles to help us figure out these values. When we're making our triangles, keep in mind that x represents the ratio of sides based on where g inverse of x is the angle that we are using to label the sides of the triangle. So what do I mean by that? If we look at the sine inverse, recall that sine is opposite over hypotenuse. So our ratio for opposite over hypotenuse in our triangle that we're going to make is 1/4. Now, this is going to allow us to start to make a picture. Now, as we make our picture, we're not just going to draw any triangle anywhere. I do want to think about quadrants at the same time. So we do want to pay attention to the quadrant that g inverse of x will be in. Since we're evaluating sine inverse of 1/4 first, that means our angle that sine inverse of 1/4 represents would either be in quadrants 1 or quadrant 4 because of the range of sine inverse. Since we're trying to evaluate sine inverse of a positive value, sine is positive in the first quadrant. So I'm going to draw my hypotenuse or terminal side in the first quadrant. This angle down here would be the sine inverse of 1/4, and there's our triangle. Now here we have a choice of opposite and hypotenuse for our right triangle. As long as opposite over hypotenuse is 1/4, we can pick any values we want. But the easiest choices would be to make our opposite of our angle 1 and our hypotenuse 4. Now that we have a triangle drawn, we're going to find all the sides of the triangle, at least the ones that we need, and then evaluate the f of g inverse of x based on the triangle and the definition of that. Since we're trying to evaluate cosine of this angle, cosine is adjacent over hypotenuse. Currently, I don't know the adjacent side of my triangle. But if we use Pythagorean theorem, our adjacent side will be the square root of 4 squared minus 1 squared, or the square root of 15. Now, to evaluate, our cosine of sine inverse of 1/4 would equal the adjacent side in our triangle, which is root 15, over our hypotenuse, which is 4. So cosine of sine inverse of 1/4 is root 15 over 4. Next, we're going to evaluate sine of tangent inverse of negative 3 over 5. Just like before, we want to start off by drawing a picture. Now, where should I put the hypotenuse in my triangle? Since tangent inverse has a range of negative pi over 2 to pi over 2, then our angles are either in quadrant 1 or quadrant 4. Since we're trying to evaluate tangent inverse of a negative value, that means we're trying to figure out an angle for which tangent would be negative. So between quadrants 1 and quadrant 4, the only quadrant of those two where tangent would be negative is in quadrant 4. So let's put our angle down here, looking like it's in the 4th quadrant. Now, thinking about what tangent represents, tangent is opposite over adjacent. Now, even though we're thinking of sides of a triangle, we want the opposite and adjacent to be 3 over 5. So we are going to think very carefully about signs here, which is why we want to pay attention to what quadrant our inverse trig function would apply. If we look at what the opposite and adjacent side are, opposite side is our vertical side down here. Since our vertical side is going downwards, that means we're going to make this side negative. Our adjacent side, since it's on the positive x-axis, that is going to be made positive. Now, as for our quantities for opposite and adjacent, as long as their quotient is negative 3 over 5, we could pick whatever we want. We'll make our opposite 3 and our adjacent 5, just because that's the easiest numbers to pick. If you wanted instead, you could have picked 10 and negative 6, because if we still do opposite over adjacent, we would still get negative 3 over 5. But you just want to make sure your signs are in the right place, because it will help you evaluate sine later. Now, sine is opposite over hypotenuse. I already know the opposite is negative 3, but what is my hypotenuse? My hypotenuse using Pythagorean theorem will be the square root of 5 squared plus negative 3 squared, which is the square root of 34. So our sine of tangent inverse of negative 3 over 5 will be equal to opposite, which is negative 3, over adjacent, which is root 34. And our answer here does make sense when we consider what the sine of an angle in quadrant 4 will be. Recall in quadrant 4, sine is negative. Tangent inverse of negative 3 over 5 is in quadrant 4. Therefore, sine of an angle in quadrant 4 should be negative, which is precisely what we have. Next, we'll evaluate cosecant of cosine inverse of negative 4 over 7. Just like our previous problems, we want to start off by drawing a picture of a triangle. Now this time, we're dealing with cosine inverse. Cosine inverse of a value represents an angle in either quadrant 1 or quadrant 2. Since we're trying to take the cosine of a negative value, that means we're trying to find an angle such that cosine is negative. And we know our terminal side is in the second quadrant. So here we're going to put our right triangle. And because of the positioning, we're actually going to more think about reference angles. So we're going to treat this as our angle cosine inverse of -4/7, but technically it's more of the reference angle, but it'll still get the job done if we pay attention to signs. Cosine is adjacent over hypotenuse. So the -4/7 would represent the ratio of adjacent over hypotenuse for the triangle we just drew. Now our adjacent side would be the horizontal side. Since our horizontal side is drawn to the left, we'll make that length -4, and our hypotenuse, which is our terminal side of our angle, will be 7. Now to evaluate cosecant at this angle. Cosecant is hypotenuse over opposite. We don't quite know the opposite side yet, but we can figure that out with Pythagorean theorem, and we get that the opposite side is √65. Now we can evaluate cosecant at our angle. Cosecant is hypotenuse, which is 7, over opposite, which is √65. And when we rationalize, we get 7 √65 over 65. Notice that cosine inverse of -4/7 would represent an angle in quadrant 2. Cosecant, just like sine, its reciprocal, are both positive in quadrant 2. So it makes sense that our answer was positive. Now we're going to evaluate expressions where we compose a trig function and an inverse. So here we're trying to simplify cosine of sine inverse of x/3, where -3 is less than or equal to x, less than or equal to 3. The fact that x is between -3 and 3 is just to guarantee that our composition will be defined. We're going to primarily just focus on evaluating the cosine of sine inverse of x/3, very similar to what we did in the previous problem. The issue is drawing our picture. Because x is between -3 and 3, that means x/3 is either going to be positive or negative, or potentially even 0. So it's going to be hard to draw our picture for our triangle because our sine inverse of x/3 is going to be in quadrants 1 or 2. But it doesn't matter what quadrant we're in. If we draw our triangle to look like it's in quadrant 1, because we know the input of sine inverse is opposite over hypotenuse, if our angle is located down here, similar to what we did in the previous problems, we can make our opposite x and our hypotenuse 3. Now, as for our adjacent side, whether we draw this triangle that I've drawn in the first quadrant or the fourth quadrant, the adjacent side would lie on the positive x-axis. So our adjacent side is going to be positive. And if we use Pythagorean theorem to help us figure out the length, we would have the square root of 3 squared minus x squared, which would just be the square root of 9 minus x squared. And cosine is adjacent, which is 9 minus x squared, over hypotenuse 3. Now, the sign of our answer does make sense. This is because, again, sine inverse of x/3 is in quadrants 1 or 4. Cosine in quadrants 1 and 4 is always going to be positive. The square root of a number is positive, and we divide by 3, it's positive. So the signs are still working out the way we would expect with our quadrant rules. Next, we'll simplify sine of tangent inverse of 4x, where -1/4 is less than or equal to x, less than or equal to 1/4. Again, the domain isn't going to be what we focus on. We're going to focus on our composition. Just like with sine inverse, tangent inverse is in the first or fourth quadrant. So we're going to draw the triangle similar to before and think about the signs later. If we place our angle down here, tangent represents the opposite over adjacent. We can think of the 4x as 4x over 1, in which case the opposite is 4x and our adjacent side is 1. And if we think about the fact that we are in the first or second quadrant, our horizontal side, which is the adjacent side, would always be positive because we're on the right half of our corner plane. The 4x could vary in sign, it could be positive or negative, which is perfectly fine. Now, sine of an angle is opposite over hypotenuse. So now we can find our hypotenuse. No matter what, hypotenuse in our triangle represents the distance our point on the terminal side is from our center. So our hypotenuse, no matter what, we will always keep positive. So throw in our values into the Pythagorean theorem, and we get that our hypotenuse is the square root of 16x squared plus 1. So what is sine of our angle? It is opposite 4x over hypotenuse, which is the square root of 16x squared plus 1. Next, we're going to solve for theta in each of the following triangles. And we're going to present our answer in both radians and degrees. Most of the times when we're working with triangle problems, we are going to leave our answer in degrees since that is the most common way to measure angles in a triangle. But we're also going to practice with using the calculator at the same time and making sure we're careful with settings. Very similar to the problems we were working on last unit. We want to identify which trig function to use in order to set up an equation. In order to identify the trig function, we need to label the parts of our triangle based off of the angle that we're trying to solve for. So looking at the first triangle, our side of length 6 will be the hypotenuse, and the side of length 5 we see is the opposite side of theta, so that is the opposite. Which trig function relates opposite and hypotenuse? That would be our sine function. So sine theta would equal 5 over 6. But remember, our goal is we're trying to solve for theta. And since we're dealing with right triangle problems, we know our angle is acute. So if sine theta equals 5 over 6, thanks to our definition of inverse functions, theta will equal sine inverse of 5 over 6. Now from here, we'll go to our calculator to evaluate. If we were to evaluate our angle using radians, first, make sure our calculator set the radians. And if we go to function, we can find our 3 inverse trig functions. Click on sine inverse, then we can enter our input. And we can see in radians, our angle is approximately 0.9851 radians. Now, if we want our answer in degrees, all we have to do is just switch our calculator here in Desmos to degrees. So in degrees, our angle is approximately 56.44. Now, for our second triangle, the side of length 2 is the opposite side. Our side of length 5 is the adjacent side. Since we're working with the opposite and adjacent sides, that tells us we should use the tangent function. Tangent theta would equal opposite 2 over adjacent 5. Since tangent theta equals 2 over 5, that means theta will equal tangent inverse of 2 over 5. Going to our calculator in radians, so we'll set our calculator radians, click tangent inverse, enter our input, and we get that theta is approximately 0.3805 radians. Now for degrees, switch our calculator to degrees, and we get that our theta is 21.80 degrees. Now for our last triangle, the side of length 15 will be the hypotenuse, the side of length 2 would be the adjacent side. So which trig function should we use? We should use cosine because we're working with the adjacent and the hypotenuse. So cosine theta is equal to 2 over 15, which means theta equals the cosine inverse of 2 over 15. Now we can go to our calculator. First, for the radian measure, cosine inverse, switch our calculator to radians, and we can enter our input. We get that theta is approximately 1.4371 radians. For degrees, switch our calculator to degrees, we get approximately 82.34 degrees. For our next problem, from the top of a tower that is 100 feet tall, a guide wire that is 100 feet long is attached to the ground to the top of the tower so that there is no slack in the wire. What is the angle between the ground and the wire? Just like in the triangle problems we looked at last unit, we want to start by drawing a picture. So the horizontal line will represent the ground, the vertical line will be our tower, and this red line will be our guide wire. Since the problem says there's no slack in the wire, that just means the wire is a straight line from the top of the tower to the ground. Now let's label our measurements. Our tower is 100 feet tall, the guide wire is 400 feet long, but we don't know what the angle between the ground and the wire is, and that is what we're looking for, which we're going to call theta. So what we've just created through our picture is a right triangle, and the reason why it's right is because the tower is perpendicular to the ground. Now, just like in the previous problems, we will label our sides. The side of length 400 is the hypotenuse. The side of length 100 is the opposite side. Since we're dealing with the opposite and hypotenuse, then we want to use the sine function to set up our equation. So sine theta equals 100 over 400, which means theta equals sine inverse of 100 over 400. Even though the problem doesn't state what units we should use for the angle, whenever we're dealing with geometry problems like this, it is standard practice to use degrees. So when I type the sine inverse of 100 over 400 into a calculator and making sure it is set to degrees, I get that our angle is approximately 14.48 degrees.